quantum transport, that is quantum mechanics plus transport. Transport generally in physics refers to electrical transport or transport of charge carriers such as electrons or holes through the system. Now, when we say quantum transport, it actually means the manifestation of quantum nature of electrons in transport. Now, you might ask, all right, but many of the properties that we use in the transport, such as band gap, effective mass, these are all derived from quantum mechanical nature of electrons. That is true, but those are electrical properties. Those are material properties. But when we say quantum transport, we will observe the quantum nature of electrons, whereas the classical transport still treats the electrons as particles. But even though the properties are derived from quantum mechanical principles. Before we get into the details of the quantum mechanical nature of electrons, let's take a quick look at the classical transport. Okay, the transport study or the electrical transport study generally refers to the measurement of current as a function of voltage or voltage as a function of current. But you can actually do this characterization or this measurement as a function of various other parameters, such as the magnetic field, the applied magnetic field, the applied electric field. There can be another electric field in addition to the field that you are applying to drive the electrons through the system. It could be strain in the material or as a function of the intensity of electromagnetic radiations on the material. These are all transport studies. Okay, but now when we observe the quantum mechanical or wave nature of electrons in transport, then we say we are in the regime of quantum transport. Okay, in classical transport, let's consider a very simple device. Probably the simplest device that you can have is a resistor. It's a piece of material with certain resistance. Resistance is nothing but the ratio of voltage to current in the material. Okay. What I have here is a picture where the electrons are considered as particle which is undergoing various collisions with imperfections in the lattice, various things in the material. Okay. Now, the picture here is you basically consider electrons are particle. They undergo collisions with various collision center in the material. I'm not going to define what are those collision centers at this point. There are details to it. Okay, this is just an overview. Now then electron will lose energy as it moves through the material because it actually loses energy. That means it is going to lose its speed also at the same time. So there will be a statistical nature for this transport. So there will be some velocity v, is an average velocity, it's a statistical number again, when you apply an electric field E across the material. Then electrons will move from one end to the other end. This movement is somewhat analogous to the movement of grains of sand through a hourglass. You can consider this resistance as the small constriction at the middle of the hourglass, where the motion through the whole system is defined by this constriction here, where the fan is going to move through a lower velocity because it collides with each other and also collides with the poles of the container. This is the general or the statistical or the particle nature or the classical transport picture what we have for motion of the charge carriers. In this case, those are electrons through the system. Okay. Now, but when we consider the wave nature of electrons, we need to consider what effects that's going to bring to the classical or this picture of transport. What I have here is two landmark experiments. One is a scanning tunneling microscopy image of 48 iron atoms on copper. They are arranged in the shape of a ring. It's a very sophisticated experiment. And here is the approximate size of the ring, around 12.4 nanometer. Okay. And what you are seeing here is a plot, a three-dimensional plot or the three-dimensional image of the wave function of the electrons on the copper surface. These iron atoms are arranged on a copper surface. And you can see this is very similar to the standing wave patterns or the ripples that you are going to observe in a coffee cup or in a cup where you have some kind of liquid, coffee or any soft drink or water or anything. So what you are seeing here is the manifestation of wave nature of electrons in this case. This is going to set up, the wave function is going to set up ripples just similar to that of on the surface of the water or a liquid. Another experiment is the propagation of the electrons through a narrow constriction. This is similar to the propagation of water waves through narrow constriction, which is shown here. The white colored region defines the small constriction where the electrons are going to travel through. As it travel further away from the constriction, you can see it's going to set up ripples or wave nature, which is here in this case is captured by a scanning probe microscope, which is going to sense the ripples on the wave function of the electron distribution, very similar to this measurement. So what we are seeing here is the picture that you are going to get is very much different from the picture what you have here for the transport of electrons through a resistor, which is just a particle picture, which is similar to the sand grains moving through an hourglass. Whereas in this case, it is more close to the water waves. I mean, this is just an analogy, but there are a lot of details to it. And there are a lot of variations to this very crude picture of water waves to it. Okay, but those things we will address in detail as we move further. Okay, so what I am trying to say is you have completely contrasting pictures when you consider the wave nature to that of the particle nature. And in this course, what we are interested is to understand the nitty-gritty or the details of this quantum transport and see how we can observe many of these interesting new phenomena and how can we come up with or how can we use these phenomena for novel devices. This is more or less a device physics course, but in the premise of quantum transport. Now, when we talk about the device physics, we need to understand, or we need to get some historical details of devices. Here, we are looking into the first, probably the first electrical device, that is a switch, or we call it a relay, or it's a bistable device. Okay. So what you have is you can open or close a switch by the application of current through a certain coil. That is what is shown here. This is invented by Joseph Henry in 1830, and this is an actual picture of that device. This is a big macroscopic large piece of device with an electromagnet. When we apply current through this one, this is going to create a magnetic field which is going to pull this arm and eventually will close the circuit. So you can switch on or off the circuit, this circuit, by the application of current, which will create a magnetic field. This is just a bistable device. This has two states, either on or it's off. And this switch or this relay, this electromechanical relay, has revolutionized the then communication technology, which was a telegraph. What you are seeing here is the picture of a Morse key sounder by which you are going to send messages. It has also only two states, a long press or a short press. Okay. And the picture here is Professor Morse sending the first telegraph message, which is what had God wrote. It's a statement from, it's a sentence from Bible, the Holy Book Bible. But the meaning is, it's amazing, right? That is the meaning of it. And that has been transmitted from Baltimore to Washington over a telegraphic line. And this is the picture we're showing that occasion. So as you can see, the first device, electrical device, is simply a electromechanical relay, which has revolutionized the communication industry, the communication technology then. And nearly or more than 100 years later, you have another switching device or another bistable device, which is a transistor, revolutionizing the whole technology, which is responsible for the technology that currently we have. It is a transistor, okay, invented in late 1940s, and Nobel Prize was awarded for that invention in 1956. It's a big piece of semiconductor. When I say big, it's like 1 centimeter in size. And transistors are the backbones of every semiconductor chip or every semiconductor technology that we are seeing. This transistor is approximately 1 centimeter in size, whereas the current transistors in the latest generation of processors are approximately 7 nanometer in size. Now we started from 1 centimeter and reached like 7 nanometer in a span of approximately 70 years. It's a huge size reduction revolution. That is what we are seeing over these years. So this chart shows a plot of how or the sequence of this revolution, how this has happened. And I have marked major milestones here. Those refers to major technology breaks or major technology inventions or upgradation over the year. And currently we are at 7 nanometer size. When I say 7 nanometer, what that means is the smallest repeating dimension inside it. It could be the size of the gate, size of the channel. I will get into detail what we mean by channel and all this in a minute. Okay. We started with something 1 centimeter and we reached something of the size of 7 nanometer. Okay. And I have roughly divided this into 3 regions according to the size. So I have something called macroscopic regime, where the size is like a few micrometer or larger. And I have something called microscopic, where something like a few nanometer or smaller. And there is something in the middle that is we call mesoscopic. Mesoscopic actually means neither macroscopic nor microscopic. It is somewhere in the middle. Now, you can see here, as the size of the technology reaches the mesoscopic regime, the whole development has been interlaced with various inventions in fundamental science or in fundamental physics, almost all of which have quantum mechanics at its base, at its bottom. Okay. Superconducting tunnel junctions, two-dimensional electron gas, two-dimensional electron system. SDS means Subnikov-Dehas oscillation, quantum Hall effects, fractional quantum Hall effect, GMR, giant magneto resistance. Almost all of this actually was considered as major inventions in the field of physics, and all of them have awarded the Nobel Prize also. Okay. Now, the latest 2 milestones what I have here, or inventions here, though are technology developments, but those are deep rooted in quantum physics, the quantum processor. So we have now reached a regime where the future processors need to be operating on quantum logic rather than the current classical logic. So what we are seeing here is a very strong cultural exchange, or a very strong scientific and technology interactions, give and take, between the fundamental science and the advanced technology. The developments of technology which has driven the large processors into the nanometer range has also enabled the scientific community to probe smaller solids in lower and lower dimensions, or smaller and smaller in size, right? Now, at the same time, the development in fundamental physics also has enabled the technology to come up with newer and newer products. For example, the development in two-dimensional electron system has caused higher mobility transistors. The development in, or the invention of the giant magneto resistance material has come up with ultra compact hard drives, GMR, giant magneto resistance material, and so on. Similarly, various other developments, okay, are always supported by science, and science is always supported by the developments or drive in this technology. So the transport in this range, mesoscopic range, has always an interesting flavor of quantum mechanics. And in this course, what we are going to do is we will address most of this phenomena and address some of this in detail too. Okay. Now, when we talk about electrical devices and transport, this technology or this term MOSFET, metal oxide semiconductor field effect transistor, MOSFET, is something we always have to refer to, or we always have to understand, without which we cannot discuss this course, or we cannot go further. These MOSFETs are the fundamental building blocks of all the processors that you have seen. Now, the next couple of minutes, we'll just look into the operational principle of a MOSFET with minimum details. MOSFET is actually a switch. It's a switch. That's all. It has two states, 0 or 1, or off or on. That's it. It has only two states. What you have here as a MOSFET is a piece of semiconductor. In this case, it is p-type, and you have some contact region which are n-type. I have put it n plus. What that means, it is heavily doped. And I have third electrode, which is something called a gate here. With the application of electric field on the gate, I can create a layer of conducting region here. Okay. So normally, if you don't have the gate voltage, then these two regions are not connected and there is no current flowing through this. But the moment you apply gate voltage, there is a channel developed and you have current flowing through it. Okay. So this axis here in this plot is Vg and this axis is current. So when you have no gate voltage or low gate voltage, the current is pretty much off, 0. And when you apply gate voltage, that is in this range, you have current, high current. So you can see this like bistable device. There's an off state that corresponds to this, and there is an on state that corresponds to this. There are two state on or off, right? And that state is controlled by the gate voltage Vg. That means this is again like a relay where you have conduction, or you have a connection between these two n regions depending on whether you have gate voltage there or not. Depending on the gate voltage, you will get either an on state, or if no gate voltage, is an off state. So it's actually a semiconductor switch. That's what it is. It has actually two states, on or off, or 0 or 1. And this is what is there in all the processors or all the technology that you're seeing today. Okay, this is responsible for the zeros and ones in your computer or laptops or cell phones or whatsoever. Okay, now these MOSFETs, metal oxide semiconductor field effect transistor, these MOSFETs have revolutionized the semiconductor industry. So what we have here is one of the first MOSFET and a small integrated circuit which comprises of 16 MOSFETs, which is made something like 60 years back, late 60s. Okay. And this technology is slightly different from the first transistor, which was made 10 years back then. which was a junction transistor made in a semiconductor material called germanium, whereas these MOSFETs are done in silicon. There are a lot of technological advantages of silicon over germanium, which we will not discuss much in detail here. What I want to point out in this case is, if you look at what is the size reduction which has happened over 60 years, is almost like we have 10 micrometer approximate size for the dimension of the structure, whereas we have something like tens of nanometer. That means 1,000 times smaller, okay, the lateral size. This is a small portion of an integrated circuit which comprises of the transistors and all the connecting lines and everything together. You can see how densely it is packed. Okay. So as I mentioned in the previous slide, these MOSFETs are like switches. Okay. It has two states, an on or off state. So by the application of the voltage on one of the terminals, which is called gate, you can have a current flowing through the circuit. Okay. When the gate is off, there is no conducting channel here and the current is zero. So we can visualize this the following way. So you have some kind of energy landscape where you apply a small voltage, that is EV, which is mentioned here. And though we have applied a small voltage, but you won't get any current through the system or for current through this device, because there are no conducting channel in the middle, which you can visualize as a barrier for the current. And when you apply gate voltage, you will get a conducting channel. Then that is equivalent to saying this barrier is lowered, something like this, so that current can go through this. So you have a barrier when the gate voltage is zero, and you have no barrier, or you have conducting channel when the gate voltage is substantial, or when you apply gate voltage. So those are your two states, the on and the off state. Now, in the process of reducing the channel dimension, what you are effectively doing is you are also reducing the distance between the source and the drain. So you are making the whole structure here really thin. Okay. Now, when you do that, you are also going to reduce the width of the barrier as shown here. This is just a cartoon, just to visualize what is happening. Now, remember, when you make the barrier really, really thin, at some point of time, you don't have a well-defined off state. Means when it's very thin and you are applying a voltage here across the barrier, this voltage is basically applied across this barrier. Okay, so you can have a leaky path from the source to drain, because the barrier is not thick enough. It's not able to stop the electrons completely when you apply bias. That is equivalent to saying that you have something like a tap. The closed state of the tap is like the off state, and when you turn it on, it's on state. But you have, at some point of time, you have seen taps which even if you close it completely, still water will drip. So it's a leaky tap. It's a leaky tap. Okay. So you can have a situation when you reduce the size too small, you can have leaky path, or you cannot shut down it completely. So for you're supposed to be here, this is your off state and this is your on state. But since you have a leaky tap or leaky system, your off state will be somewhere here because you still have a non-zero current when it is off. So this is equal to saying that you don't have a well-defined on and off state. Okay, and you can actually work out what would be the minimum dimension, that is the limit for scaling, that is called scaling limit. Okay, the minimum dimension that we call lambda, that is given by this formula where epsilon channel is, these are the dielectric constant which defines the field strength, okay, divided by EOX is the dielectric constant of the oxide layer, and DCH and D oxide as the channel and dielectric constant thickness. So for silicon, this is approximately 10 nanometer, and you can see that we are almost in that regime. So the current technology is 7 nanometer, the previous technology was around 10 nanometer, so we are almost in that regime. Okay, so what we are trying to say here is we are almost in the limit of this scaling. Okay, so what are the issues? We already looked into one of the issues, that is you don't have well-defined on or off state, or you can have leaky systems. Okay, now second issue is something which is related to the uniformity of operation. Remember, as you increase the number of transistors or reduce the size of these transistors, you are reducing the size of the active region. And remember, you have dopants in the system which are randomly distributed. Though they are uniform, but they are also random. Okay, this is like something similar to what is shown in this illustration here. Okay, now remember, if you have something like a 42 nanometer wide gate, okay, and 24 nanometer long, okay, if you have something like that, an active region which is of that dimension, for that you can say that you have approximately something like few tens of dopants underneath the gate. Now remember that these transistors consist of, these wafers or these chips consist of billions and billions of the transistors, and it is not very easy to maintain the uniformity over the entire area where this number of dopants are same pretty much everywhere. If you have say 1000 dopants and if they vary by 1 or 2, that's a very small fraction. But if you have 36 dopants as mentioned here, or if you have 20 dopants, and if you vary by few dopants, that's a huge fractional change when you go from one device to other device. So there is an issue, or there's a huge trouble, or there is a lot of hardship in maintaining the uniformity of performance over the entire wafers. Okay. Now, whatever the reasons or whatever the issues that we discussed previously, whether it is actually a leaky path or it's a non-uniformity issue, these are all classical issues, or these are issues created by classical physics, or these are not connected to the topic, that these are not entirely connected to the topic that we are going to discuss. But there are really interesting problems. Those are put forth by the quantum effects of the quantum mechanics. Now, the overall exercise that you are doing is reducing the size. Okay, whether it is the thickness of the oxide or whether it is the channel length or whatever it is, you are reducing size overall. And quantum mechanics has some very interesting phenomena which is called tunneling. So even if you try to stop the electrons by creating a barrier, but you have a non-zero probability to have the electron tunneling through the barrier or traversing the barrier. Okay, and there is a transmission probability over classically forbidden regions, which is exponentially dependent on the length of the exponentially dependent on the length by this formula. What that means is really short lengths, you have a substantial probability for tunneling through the barrier. Just note that there is a negative sign here. Okay. Now, that is one way. Second thing is, when you reduce it really thin, the gate oxide, you can also have the gate injecting carriers into the channel by quantum mechanical tunneling. This is not related to non-uniform gate oxide or gate insulator where the carriers actually leaks to the channel. This is a quantum phenomena what I am mentioning here. Okay. So tunneling is an interesting though but a serious problem which has its origin in quantum mechanics when you reduce the size. Now there is even a more interesting problem that comes from the confinement driven quantization or confinement driven discretization of energy values. So this cartoon here shows a typical MOSFET where you have a source region and you have a drain region and they are connected through some channel which I have shown here by the blue region. Okay, and the source drain characteristics or IV characteristics here, VSD versus the current, you will get something like this curve as shown, and these are two IV curves which are shown for different gate voltages. This is for one gate voltage, this for another gate voltage. There's two curves here. Okay. Now the action of you reducing the channel, this dimension, into the quantum regime or into really small dimension, when I call quantum regime is really small, something like a few tens of nanometer, then your introductory quantum mechanics says that when you make something very small, you can have discrete number of allowed states inside that. When you have a large region, you have a continuum state. States are continuously distributed. But when you make it very small, you can have discrete number of states and which are given by the something. This is just a toy model, particle in a box, but that is not always applicable. This is just to give you a feeling of the discreteness. Okay, this particle in a box is only a toy model. This is not always applicable. This is generally not seen. Okay, these potential wells have different shapes other than not other than the square shape. Okay, but the point here is you have discrete states and discrete energy levels. So you don't have a continuum state as described in this case. Let's consider that in case of a classical system, you have continuum state here. Okay, it's all throughout field. Okay, because you know the spacing between the levels is inversely proportional to the size L. L is the size of the well. So when you have a large L, the spacing between these levels will reduce and you will eventually get a continuum state. This is source, this is drain. Okay. But the moment you reduce the size, what you are going to get is discrete number of states. And when you have discrete number of states and when you try to apply a voltage and measure the current, that is your IV here, you may not get something like this as you seen in the classical case. This is the classical case. Okay. Because what you are doing in this specific case is you are increasing the window, this window between the source and drain. Okay. Now, when you increase the window, in this case, you are continually increasing the number of states available for transport. But in this case, you are increasing the states one by one because your states are far separated and you will increase state in a discrete manner. What that means, the total current also can change in a discrete manner. Again, this is a toy model. So current will go like this in a stepwise manner. That is what is expected. So in this case, you don't have the typical MOSFET behavior. It is quite different. Okay. Now, this is another effect of quantum mechanics playing in. Now, let us relook the charge transport in terms of the electrons going through circuit. So, charge transport in terms of electrons going in a discrete manner. So what we generally define is a current, and we think it is a continuous quantity. Current at some point of time is certain ampere, and that is kind of maintained uniformly. But current is not the fundamental quantity here. What is fundamental here is a charge, which is going through circuit at certain interval delta t time. So current is nothing but the charge, E is the electronic charge and N is the number of electron going per unit time. Okay, going per certain amount of time delta t. But remember, these electrons are discrete packets of charge. They don't flow continuously. Though you can represent them by nature, but they are discrete packets. Okay. And when they go through something like a classical device, for example, a resistor, there is a statistics playing there. Okay. So what you are saying here is, at every moment, every time interval delta t, there are a certain number of electrons going through the system. At some point of time, it could be, say, 100. Next moment, it could be 101. The next one could be 110, maybe next 99, 98. But on an average, they are all around certain number. Then there is an average number, that is n here. So this plot here shows the number as a function of, it is actually a histogram. It shows the number n if you take a snapshots of every second, what is the probability of seeing certain number n? That is this plot. Okay, what is the probability of getting certain number n? And the probability of getting a very low number and very high number are kind of very low, because there is a statistical behavior, it has a statistical behavior, and more or less every time, then if you define the current and the resistance value, then on an average, if you define the voltage and the resistance value, on an average, same current flows through it. When I say same current, the number of electrons are more or less same. But I'm not saying it is accurate, the same number every snapshots or every instance of interval delta t. If you take measurement 1, measurement 2, measurement 3, most of the time you will be in this bracket if this is n. This n is nothing but its average number which is going through it. Now, this is a statistical distribution, and there are other properties for the distribution, such as the higher moments of the distribution, like kurtosis, which is sharpness, skewness, how symmetric this distribution is, hence the variance, the width of the distribution. And when you measure this current, you are losing a lot of information regarding the higher moments. And these higher moments have a lot of importance when you consider lower systems or lower dimensional systems, where this electron-electron phenomena such as electron-electron interaction, correlation, and all these things are actually now we are missing when you measure only the current. When we say correlated transport, first of all, let's look into what is an uncorrelated transport, just by a simple example. People walking on a street in a market. You can say, or people randomly crossing over the road in a market. If you stay there at some point stay there for the whole day and measure it, you will get a certain average number. And what you would see, there is no correlation between the people who crossing the road or walking each other. And what that means is there is an average number and there is a distribution to it. Okay, and there is nothing interesting. It's more or less, it will be symmetric distribution. But at the same time, an army marching, there's a perfect correlation between the people, and you can very sharply say that, okay, this is a speed, this many number of people, this many number of army men have crossed certain point. Okay. And another interesting point here is, here you have, it's a noisy system. Noisy system, when I say noise, means the noise in the number of electrons. For a solid, here the noise in the number of people. If you fix an average number, say n, crossing the road, how much that number of people crossing the road is changing every second from the average number. How wide the distribution is. If I say n people and what is the width of the distribution, there is a noise to it. Okay. Now, since there is no correlation between the people crossing the road and this width of the distribution will be actually proportional to n. Okay. That is a noise to it. That is a noise when we inspect electrical systems and associated quantity called noise to it. That is the noise. Okay. That is the randomness. Whereas when you have a perfectly correlated system which does not have much noise, so in that case I can say, okay, n number of person cross at every time, every instant, it's the same n. There is not much width or distribution. That means there is a noise bunching. Okay. The correlation between the electrons, here in this case, the correlation between the people, mesoscopic systems, low dimensional system, where there exists a perfect correlation between the transport of charge carriers. Those have very interesting property systems such as charge pumps, Kondo effect. Okay, you can see suppression of the short noise. We will explain short noise at some point of time. You can consider that's a noise, electrical noise. There are interesting bunching and anti-bunching effects. You can observe all these things in correlated systems. And these things are generally not seen in large three-dimensional systems such as a resistor or a bulk piece of material like a metal or a semiconductor, unless there is some other phenomena called macroscopic quantum mechanics or macroscopic quantum phenomena. Okay, so what we have discussed so far is quantum confined phenomena or low dimensional systems can show interesting effects in transport. This is just an overview. There are naturally confined systems such as a cluster or an atom with discrete energy states. There are a lot of interesting systems. But those you cannot measure the transport using current or voltage proofs. Or you cannot measure the resistance of those systems with a multimeter. So, the systems, what we are discussing here are mesoscopic systems, or systems whose dimension is above the naturally confined but far below the bulk systems such as a resistor or a capacitor or inductor. But we are interested to do transport measurements. So what that means is we need devices or we need technology where we can go down to dimensions in the sub-micrometer scale, but not to this scale. Okay, those are too small. That is possible only with advanced device fabrication tools such as lithography tools. What we are seeing here is a wheel which is lithographed with a dimension which is given at 40 micrometer. Okay, the wheel, the sun temple wheel, which is lithographed using electron beam lithography with a size of 40 micrometer. This is the emblem of IISER TVM with a size 10 micrometer. And this is another device which is also lithographed using electron beam machine to sub-micrometer scales. So one interesting technology that we will be using all throughout for making this device is lithography, which has its origin in the technology development, the semiconductor revolution. Now, we also discuss that the quantum confinement gives discreteness, and that energy scale is inversely proportional square of the distance in this case. But you can say roughly that goes down as the distance goes up. And to observe that energy, scales or those effect of those quantization, you need suppress the thermal energy which is already there in the system. So the dimensions that we are interested is in the submicron regimes, okay, like 50, somewhere in this bracket. What that means is the thermal energy should be minimum, or that should not contribute much to your transport. That will create noise in your system. What that means is the temperature range that we are looking is in the sub-Kelvin range regime. That means you need lower temperature. So the transport study in this case for quantum confined system now puts two constraints, two restrictions. Number one, that is on the size. Number two, that's on temperature. But these are actually interrelated. To see quantum effects at room temperature, you need systems of few nanometer, but these are not addressable by your voltage and current probes. You want to be somewhere in this range to see the effect of quantum confinement. What that means is you need to be in this temperature range. That naturally tells you, one, you need low temperature. That means you need cryogenics. And second thing, it tells you you need fabrication tools which allows you to reach the dimensions of like hundreds of nanometer down to tens of nanometer. Okay.